A team of Brown University researchers has found a way to double the toughness of a ceramic material used to make solid-state lithium-ion batteries. The strategy described in the journal Matter could be useful in bringing solid-state batteries to the mass market. There is huge interest in replacing the liquid electrolytes in current batteries with ceramic materials because they are safer and can provide higher energy density. So far, research on solid electrolytes has focused on optimizing their chemical properties. With this work, the researchers are focusing on the mechanical properties in the hope of making them safer and more practical for widespread use. The electrolyte is the barrier between a battery's cathode and anode through which lithium ions flow during charging or discharging. Liquid electrolytes work pretty well. They are found in most batteries in use today. But they have some problems. At high currents, tiny filaments of lithium metal can form inside the electrolytes, which cause batteries to short circuit. And since liquid electrolytes are also highly flammable, those shorts can lead to fires. Solid ceramic electrolytes aren't flammable, and there is evidence that they can prevent the formation of lithium filaments, which could enable batteries to operate at higher currents. However, ceramics are highly brittle materials that can fracture during the manufacturing process and during use. For this new study, the researchers wanted to see if infusing a ceramic with graphene, a super strong carbon-based nanomaterial, could increase the material's fracture toughness, that is, a material's ability to withstand cracking without falling apart, while maintaining the electronic properties needed for electrolyte function. For this work, the researchers made tiny platelets of graphene oxide, mixed them with powder of a ceramic called LATP, and then heated the mixture to form a ceramic graphene composite. Mechanical testing of the composite showed a more than two-fold increase in toughness compared to the ceramic alone. The researchers explained this by saying that when crack starts in a material, the graphene platelets essentially hold the broken surfaces together so that more energy is required for the crack to run. Experiments also showed that the graphene didn't interfere with the electrical properties of the material. The key was making sure the right amount of graphene was added to the ceramic. Too little graphene wouldn't achieve the toughening effect. Too much would cause the material to become electrically conductive, which is not desired in an electrolyte. Taken together, the results suggest that nanocomposites could provide a path forward to making safer solid electrolytes with mechanical properties to be used in everyday applications. The group plans to continue working to improve the material, trying nanomaterials other than graphene and different types of ceramic electrolytes. The researchers say that this is the toughest solid electrolyte that anyone has made to date. And they also say that there is a lot of promise in using these composites in battery applications.